Hi, I'm going to talk about the lab 5, which is magnetic braking with Faraday. So the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil and model the magnet's tube interaction computationally and compare my computation predictions with my observed data. So the fundamental physical principles used here are Newton's third law, Biot-Savart law, and Faraday's law. The observed model here for the system is smartphone, bar magnet, row of aluminum foil, and the surrounding is everything else. And for the initial conditions, we have magnet mass, length of aluminum tube, width of foil, and inner radius, and total radius, mu, and average drop time. The assumption here is that the system is isolated, meaning there's no external force acting on the system. So the first main physics idea is Newton's third law, which describes the force on the falling magnet and the force by the entire tube need to be equal. The second one is Biot-Savart law, which describes magnetic field due to a current carrying conductor at a distance point is inversely proportional to the square of the distance between the conductor and point, and the magnetic field is directly proportional by the length to the length of the conductor, current flowing in the conductor. And the last law is Faraday's law, which describes the magnitude of the electromotive force EMF or voltage induced in a conductor due to electromagnetic induction. So for the brief preview of the result, the larger the mu value, the more drastic the results will be. So here's the coding parts. For coding, I've coded the magnetic field of dipole and calculated dF over dt. And finally, printed time in tube. The following is a graph of velocity versus time. For interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions, which color corresponds to clockwise and which is counterclockwise, and how can I know? So for me, the red color current indicates clockwise flow, and the blue represents counterclockwise flow. As the magnet moves down through the tube, a counterclockwise direction represents the resistance against the increase in magnetic flux. What happens to the dynamics of the system when I flip the magnet around? The answer is that when the magnet is flipped, it will still fall in the negative y direction. However, the flux will decrease in the opposite direction that it is now. How does the total time in tube of your real-world system compare to that of your computational system? How might the computation system be made more accurate? The real-world system will be more accurate because if the experiment is done correctly, I would have little room for error. And the last one, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The graph shows us that the net forces on the bar magnet sum to 0 while inside the tube. So for the first what if question, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The answer is the current would have to be larger and the magnet would have take longer to fall. The second is, what if holes or slots were cut into the tube? How would this affect the room currents in your model? If the holes were cut into tube, the magnetic force and the induced current would decrease, and these decrease would cause the magnet to drop faster. So this was the end of the presentation, and this was Esther. Thank you.